Here we go. Chapter 11, Properties of Solutions. We're only going to do a very small amount of this chapter. Most of it is not in the AP Chemistry test, and we just don't have enough time to do extra things right now. So we're going to learn what's on the AP Chem exam for this chapter. We're going to go to section 11.5, boiling point elevation, freezing point depression. So first we're going to give you some facts. Fact number 1. When a non-volatile solute is added to a liquid, the vapor pressure of the liquid decreases. This is just a given. You have to accept this as fact. So literally, if I dissolve some sugar in water, it makes the vapor pressure of the water decrease. Remember, vapor pressure is the pressure that is found if I put a liquid in a closed container and I can somehow measure the gas phase above the liquid phase, and I let them come to equilibrium, the gas and the liquid, and I can measure the vapor pressure of the liquid, of the gas above the liquid. That is called the vapor pressure of the liquid. And that pressure changes with temperature. It's one of our other facts we'll get to in a moment. Fact 2. Liquids boil when their vapor pressure is equal to the outside pressure. You need to know this. This is why when you go up a mountain, water boils at a lower temperature, because the pressure outside when you're on a mountain is lower than the pressure at sea level. Oops. Fact 3. Vapor pressure increases as temperature increases. So as we heat up a liquid, the liquid's vapor pressure increases. Hopefully that makes sense. If I put a liquid into a closed container, and I let that liquid come to equilibrium, the container's closed, I let the liquid come to equilibrium with its vapor phase, and I can measure the gas pressure above the liquid. If there's a way to do that, that gas pressure would be considered the vapor pressure. Well, if I heat up that closed container, hopefully you realize you will get more gas molecules in the vapor phase, so the vapor pressure would go up. Okay, so the consequences of these three facts are, it's a big first consequence. When a non-volatile solute is added to a boiling liquid, the liquid's vapor pressure will decrease to a value below the outside air pressure. That's because of fact 1. When we add a non-volatile solute to a liquid, the vapor pressure of the liquid decreases. So this boiling liquid, we add a non-volatile solute. You're probably wondering what that is, and I will explain it in a moment. You add this non-volatile solute to the boiling liquid. The vapor pressure of that boiling liquid is going to decrease because of fact number 1. And the liquid is going to stop boiling because the vapor pressure will go to a value below the outside air pressure. Now real quick, non-volatile solute. That just means a solid that I put into a liquid, and that solid is not going to evaporate off. That's all non-volatile just means. It's a solute that does not evaporate off. The liquid can still evaporate, but the solid that we dissolve into the liquid will not. Okay, so we have our boiling liquid, we add our non-volatile solute, the liquid's vapor pressure is going to decrease below what it was, and it was only at the outside air pressure. So that liquid would stop boiling, and in order to boil again, you'd have to heat the liquid up. So you can heat that liquid to a higher temperature to get the vapor pressure of the liquid back up to the outside pressure. But that means that the boiling point of the mixture, the non-volatile solute in the solvent, is greater than the boiling point of the pure liquid. There's a name for this whole phenomenon. It's called the boiling point elevation. So, when a non-volatile solute is dissolved in a solvent, the boiling point of the solvent increases, elevates, hence boiling point elevation. Yay! Okay. Next. We have a formula for this. Delta T boiling is I, Kb, M for molality. So let's look at what are all these things that we're talking about. Let's start with the first three. Delta Tb is our change in the boiling point temperature. It's the boiling point with a solute minus the boiling point with the pure solvent. So it's a difference in boiling between the pure solvent and the solvent with a solute. I is called that Van 't Hoff factor. It's the number of particles in a formula unit of a substance, and we will have a chart for these in a moment to help you understand better what I is. Typically, we just assume I is 1. Kb is the boiling point elevation constant. Now, there's a table. Wait, before we get to the table, what was M? It's, first off, M is an italic M. I couldn't really make an italic M with my handprint or with my printing, but that is supposed to be an italic M. It stands for molality. It sounds like molarity, but it's not. It's molality. It's moles of solute per kilogram of solvent. Molarity is moles of solute per liter of solution. Molality is moles of solute per kilogram of solvent. Now, here are a whole bunch of different Kb's and Kf's for a bunch of different substances. And the substances' boiling points and freezing points are also given. Remember now, normal boiling, normal freezing, that's the boiling point at 1 atmosphere of pressure. And normal freezing is the freezing point at 1 atmosphere of pressure. All right, let's talk about I over here, the Van 't Hoff factor. So I is, let's look at our definition of I over here. Okay, so for the Van 't Hoff factor, it's how many particles are in a formula unit. So if we look at, oh dear, hold on, NaCl, that's an ionic compound, and when ionic compounds are put in water, if they're soluble, they'll split into more than one particle. So for NaCl, we get the Na, and we get the Cl, we get 2 particles. MgCl2 is ionic, so we will get the Mg and 2 Cl's. So we will get a total of 3 particles. I would be 3. Now glucose, C6H12O6. You might be looking at that and thinking, why is it 1? That doesn't make any sense, Dr. Udell. We have a 6, a 12, and a 6. However, glucose is not ionic. When it dissolves in water, you get only 1 single particle for each particle that's put into the solution. So I is just 1. And for almost all the problems we will do, I is 1. There will be some problems where you might be asked, what would the value of I be? Okay, so let's do a problem. We put some adrenaline in some carbon tetrachloride, and let's notice up here, we know Kb for carbon tetrachloride, and we know the normal boiling point for carbon tetrachloride. We're going to assume there's an extra sig fig here for this problem, just for the sake of doing our calculation for the problem. We're just going to pretend. Okay, we want to find out adrenaline's molecular weight. So first you have to recognize, produces a boiling point. Oh, we changed the boiling point. It went from 76.8 to 77.29. It elevated, so we have to use our boiling point elevation equation. We're going to assume I equals 1 unless noted otherwise. So now let's start figuring out some of our information. Delta Tb, that is the new boiling point with the solute in it, minus the normal boiling point, 76.80, given right there. Okay, I is 1. Kb was given above, right here. And I just calculated delta TB. And we still need the molality. Now this one's a little bit tricky. Molality is moles solute. Wait, let's look back at the equation here. It's the moles solute per kilogram of solvent. So we are given that there's 36 grams of solvent, and we know the mass of the solute. You have to figure out what's the solute and what's the solvent. The solvent is always the substance that has a greater mass, always. So we have 36 grams of solvent, and molality, we put the kilograms of solvent on the bottom. We don't know how many moles of solute. We're going to just leave moles of solute alone. We do know that we have 0.64 grams of solute. So if we plug all of this information into our boiling point elevation equation, we can solve for the one missing piece, which is the moles of solute, and then we're trying to find molar weight. What's the molar weight? Molecular weight will be the grams of solvent that are given divided by the moles of solute that we find from delta T as IKBM. So here's our equation. We substitute everything in. I just substituted everything from here into the equation. And I'm going to isolate moles of solute. So we isolate the moles of solute. We get 0.0035 moles of solute. And our molar mass is just the 0.64 grams of solute, because that is how much adrenaline was put into the solution. And we know that there had to be 0.0035 moles of solute put into the solution, because that's how many moles would be needed to give the 0.49 degree change in the boiling point. So our molar mass is just the mass of solute over the moles of solute. We were given the mass, we calculated the moles, so this was given the mass. We calculated the moles using the boiling point elevation equation, and we get our final answer. All right, so in addition to have boiling point elevation, we also have freezing point depression. This is when a non-volatile solute is dissolved in a solvent, the freezing point decreases, or goes down, or depresses. So when you hear freezing point depression, you want to think the freezing point goes lower than the original freezing point. Okay. So we have an equation that looks just like the boiling point elevation equation. It's just that now we have the change in the freezing point and a freezing point depression constant. So delta TF is the original freezing point minus the freezing point with a solute. So KF is a freezing point depression constant. Let's do a problem. New problem. We are going to find the molecular weight of vitamin K. Some interesting information. Can you figure out what's the solute and what's the solvent? Remember, the solvent is always the stuff that there's a lot more of it. So hopefully you figured out this is my solvent. This is my solute, which is vitamin K. Now, this is a little bit different. The freezing point is lowered by 4.43 degrees Celsius. So they've actually not given you the original freezing point and the freezing point with a solute. They've given you delta TF here. Okay, so this piece right here is the actual delta TF. There we go. So let's write down everything we know. I is 1 because we assume I is 1 unless we're told that we have an ionic compound. We weren't told that. We're just going to assume I is 1. Freezing point depression constant is given to you. And the molality is your moles of solute per kilogram of solvent, which is 0.010 kilograms of solvent because we had 10 grams. And we have to convert to kilograms. So now we're going to plug everything into our freezing point depression equation and solve for moles of solute. And we get 0.0011 moles of solute. So our molar mass of vitamin K will be our mass of vitamin K that was given, which is 0.500 grams of vitamin K, over the moles of solute that caused the 4.43 degrees Celsius drop in that freezing point. And we know that that has to be 0.0011 moles. And we get... Okay, so now here's a problem for you to try, and the solution's going to show up in a moment. So you can pause now, or now. Pause, and I'm going to put up the solution. Okay, there you have your answer. And in case you're taking some time to check, oh, you can always pause. So we'll just go on to the next two problems, which hopefully you already have listed in your sheet. And you can, again, pause. And the solutions for these will show up in just a moment. Okay, you might have noticed that table's on the second page, not on the first page. And I added an extra sig fig in here. The value given in the table was only 80.1. So ultimately, really, if we didn't have that sig fig, then this 2 would not be here, and the delta TB would be just 2 sig figs, and we would have to write our answer as just 2 sig figs at the very end, because that delta T that we use right here should really only be 2 sig figs. I was waiting to round until the very end, so final answer right here. Okay, you're going to want to pause again, because I'm going to put up the solution for the last one. So go ahead and pause. Okay, so here's the solution for the very last problem. There was really just one trick in here, which was making sure that you got the grams of the solvent from the milliliters and the density of the solvent. That's it. Have a good evening.